So the next paper is entitled PlaneMatch, Patch Co-planarity Prediction for Robust RGB-D Registration. The authors are Yifei Shi, Kai Su, Matthias Niessner, Szymon Rusinkiewicz, and Thomas Funkhouser.
Yeah.
Thank you.
Yeah, thanks a lot for the introduction. Unfortunately, Yifei couldn't make it, so I'm kind of his replacement right now. And as you all know, of course, we have a lot of RGB-D sensors these days, and we can actually get pretty good depth estimates with very cheap commodity devices, such as the Kinect. Now, a big challenge is, of course, if we wanted to use that kind of data in order to obtain good RGB-D reconstruction. So for instance, here we see an example from Bundle Fusion, a state-of-the-art framework that takes these depth frames and the color frames as input, and it reconstructs the 3D mesh as you go. And in the last years, especially with the seminal work by Kinect Fusion, we have seen a lot of these methods coming up. You know, some of them made the tracking more robust, some of them made the spatial extent bigger, others have robust optimizations for outliers, and so on. But one of the big questions that is shared by all of these problems is, how do we find good loop closures? So for instance, here on the left-hand side, we see voxel hashing that just uses a frame-to-frame ICP, whereas Bundle Fusion uses global correspondences based on SIFT features. And that's a very fundamental question in this area. And in order to solve it, what we need discriminative features. And in the computer vision history in the last 50 years, a lot of these features have been proposed for RGB, for geometry. And we've also recently seen a lot of progress with deep learning, where we have actually learned these features, such as Lift, MatchNet, or 3D Match in 3D. Now, what's in common by all of these features, they're all key point based. Meaning that first of all, you detect a bunch of key points in a frames, let's say Harris key point detector, and then you're computing these feature descriptors, and then you're trying to find matches. The question what we want to explore in this work is, can we actually find additional primitives? So is it anything we can use aside from the key points? And the obvious primitive we thought of was planes. And planes have one of the interesting properties that, you don't have to necessarily have complete overlap between two views in a plane to match it. If you're looking at this wall here, right, we're seeing a planar patch here on this side and at the bottom here. And they might not have been seen by the same view, but if we could match those and compute a descriptor that would match those two, we could add additional constraint for loop closure detection and for other SLAM constraints. Now, using planes is, of course, not particularly new by itself, because other methods, specifically like a point-to-plane ICP, people have already used this. And people have also used global optimizations, but the main difference here is that all of these features, all of these methods, they don't have features. So what they do is they just have some local, computation where you map, for instance, points to another frame, and you need a very good initialization. So that's not good enough to do global correspondences. So what we want to explore is actually these long-term constraints, what I said. So for instance, if you're looking at the floor here, right, we could kind of recognize that all of this floor here would be the same plane, and if so, we could add this constraint to our SLAM system. So the task we're introducing in this work is coplanarity matching. And coplanarity matching could be very well defined. Essentially, what we could do is we have a bunch of views. They see possibly a shared plane, such as this wall here. Even though there's no overlap, we could possibly detect that these are on the same plane. Now, assuming we had this, we can then integrate it into a SLAM system. Now, with PlaneMatch, we are thinking about how can we actually learn these features? How can we learn these coplanarity descriptors? And of course, in an RGB-D setting, you have a bunch of data channels as input. So for instance, we could use color, we could use depth, normals, and we can also use some plane segmentation based on a standard plane extraction method. And of course, since we have a lot of progress with deep learning methods, we could learn possibly these descriptors. And that's what we want to explore. And in order to do that, we're proposing a Siamese network architecture. First of all, we're starting with a 3D reconstruction. From this reconstruction, we're computing a bunch of planar patches. We're actually using local and global context around these patches. And then we're feeding this into the Siamese architecture with a triplet loss. So essentially, we have this local and global context. We're feeding these in the Siamese towers. And we're computing a triplet loss. And as an answer, we're getting whether it's a match or it's not a match. So I wanted to look at this a little bit in more detail. Specifically, I want to look at this first stage, where we first extract the planes. So we use the RGB and the depth data in order to get there. Second, we look at the at a given patch now. For each patch independently, we're looking at the surrounding area. So we kind of have a relatively large area for this global part. We compute a global representative feature in this case. So we're using the RGB data, the depth data, the patch mask. So basically, we are marking these pixels here around as on the plane, and we're using the surface normals. And we're doing the same thing for local context, so we just zoom in and have kind of a multi-stage hierarchy here. Now, we're taking all of this data now, and we're feeding it into these Siamese towers. So we have a local tower and a global tower, again for each Siamese tower. And each of these towers gets basically these 4 input channels as input. We first have a bunch of ResNet blocks for each of the channels independently. Afterwards, we concatenate these features, have a bunch of more ResNet blocks. And then at the end, we concatenate the local and the global tower with a fully connected layer. And for every planar patch, we're extracting a feature descriptor of 256 dimensions. Yeah, and then at the end, we put it together as we've shown here. So we have now, the local towers, the global towers for some anchor. That's the query point. Then we want to find positive and negative matches at training. And at test time, we want to answer whether there's a match or not. The big question is, of course, how would we train such a descriptor? Basically, how do we get the training data? And the nice thing is, if we are in a 3D setting, we can use self-supervised learning. And specifically, what we did here is we used the data from the scanner database. That's about 1,500 RGB-D scans. So these frames and these scans have already been pre-aligned. So we have the poses. And what that gives us, we can just, for one given frame, we can extract a plane. We can take another frame, we can again extract a plane. And because of the 3D poses that we have, we know whether these planes match or not. So with the self-supervised learning trick, we essentially extract 10 million triplets here. So we have anchors, positive and negatives. For the triplets itself, we have to make sure that we actually make good decisions of how we choose the triplets. So we take the anchors, we take the positives, and for the negatives in particular, we do hard negative mining. So we're choosing very challenging negative cases in order to make sure we can learn a very, very strong descriptor, because we make the training harder for the descriptor. That means the descriptor will be stronger at the end and better at test time. In addition to the training, we're proposing a benchmark for this new task of co-planarity matching. Here we have 6K positive and 6K negative matches. So it's always a pair, and the benchmark, the accuracy tells us how many of them could we match. And we divide this benchmark into various patch sizes, various distances, in order to reflect the difficulty of the plane matching task. If we compare this to a bunch of baselines, so here we show a comparison for precision recall curve for SIFT. So we compute a SIFT descriptor for a patch, we try to match it. That's the weakest baseline in this case. We use a color histogram, that's the green curve. And then we're using also the 2 middle ones here. These guys here, they're learned descriptors, but based on key points. So they're existing key point descriptors based on the planar patches. And as we can see, the interesting thing is if we actually use these planar descriptors, we get a much, much better precision and recall. Finally, we do an ablation study. So here we are evaluating all the different input channels and the local and the global parts. And not surprisingly, if we take all of the input channels, as well as the local and the global part, we're going to get the best performance. So you see that some of the things make actually quite a difference. So for instance, if we are dropping the mask part of our network, we don't have this planar segmentation, then the network is having really trouble to get good performance. Now, as the next thing, I would like to show you how can we actually use these descriptors. So now, we have trained them, we can test them, we can evaluate them, so we're getting pretty good performance here. Now we want to understand how we can use this in a possible SLAM system in an RGB registration framework. So what we do here is we're proposing an energy formulation, and the energy is optimizing for the transformations T, so that's all the transformations of the frames. And we have a bunch of indicator variables that I'll explain in a second. That's part of a robust optimization. So in the energy term here, we have data terms. So what we're doing is we're using the planar descriptors that we just computed. In this case, we're using a plane-to-plane distance, right? Because we have only planes. And these planes are predicted by our network. And what we're doing is we have these plane distances as D. And also we have these indicator variables S that provide the confidence for a match. I'll later explain how we deal with the confidence because they're actually free variables. Now, we don't claim that we only want to use the planar descriptors. But we want to say, oh, we combine it together, and if we combine it, it's getting better. So here we also use standard key point descriptors. It's essentially the same idea, except that instead of a plane-to-plane distance, it's a point-to-plane distance. In this case, we just use SIFT because we didn't just want to have a really simple baseline. Now, I already mentioned we have these confidence weights, these indicator variables, and these are essentially part of a lifting scheme for robust optimization. So, because if we optimize for these variables S, we could have the trivial solution by just setting everything to 0. So we need to regularize it. In this case, we need to make sure that these are not 0. In this case, we adopt the robust lifting scheme from Choi et al. So they have used this already for matching key point descriptors. And in this case, we just use the same idea here. And then we jointly optimize for all of this together, basically the T's and the S. And then the S tell us the true and the false positives at the end of the optimization. If you're looking at some of these results here, we can see, for instance, here in RGB-D reconstruction, we see a couple of patches that have been extracted and that have been matched, and we've used those in order to constrain our global optimization. If we're comparing this visually to existing work, for instance, here we see bundle fusion. At the bottom left, you see clearly that these two walls in bundle fusion, they have no overlap. So there's no view that sees basically both sides at the same time. So key point descriptors can't establish matches here. Whereas on the right-hand side, we see that our planar-based key point descriptor is planar-based descriptor is actually able to establish matches and get a very straight wall here. And there's a couple of other examples, such as here, where bundle fusion doesn't find enough matches. But if we add the planar descriptor, we're actually doing pretty well here. But of course, we don't want to just visually evaluate it. We also wanted to have a look at a quantitative evaluation. So here we evaluate in TUM-RGBD. We see here all of the state-of-the-art methods. So Redwood is Choi et al. Find the courses by Maciej Halper. Bundle fusion is our baseline. And then we see, we are about the same par as bundle fusion in terms of the error metrics here. But it's pretty interesting that we can also combine our feature descriptor with existing SLAM methods, such as bundle fusion, and adding more descriptors, and then at the end getting better alignment accuracies. What's also interesting is, if we do an ablation study here, how much do actually the coplanarity matches help compared to the key points? It's interesting that if you only use key points, you get about 5 centimeter accuracy here. 5 centimeter errors here. If you're comparing it to the coplanarities are a little bit better. But for instance, we have one scene here at the right where we only have a plane. So the coplanarity alone is not enough to constrain it. But the nice thing is we can combine both together and get the best of both worlds and setting a new state-of-the-art here. We also evaluate the long-range effects of the coplanarity pairs. So here we see we have long-range features from 1 to 5 meters. We see you get pretty good reconstructions. If you drop about half of the long-range matches, you see that at the bottom scene, you see already there's some misalignments. And if you drop them completely, the alignments are getting worse. With that, I would like to come to the conclusion of the talk. In this talk, the first thing what we presented is a new task, this coplanarity matching, and I think this is one of the first works here, and I hope there will be more. We have shown that we can efficiently learn these features for coplanarity matching using self-supervision, and we can integrate these features in a robust optimization formulation into a SLAM system. With that, I would like to especially thank the co-authors, especially Yifei, who unfortunately couldn't make it, but he did actually all the work here, and I would like to thank you for the attention. Thank you.
Thank you, Matthias. This is great. We'll open it up to some audience questions. If you just came, I see mics in the aisles. I think I counted 10 of them, although I don't see a mic in the upper balcony, so you may want to migrate down if you want to ask a question. OK, I see a question.
Nice work. What happens if you deal with surfaces that are not perfectly planar, but only almost planar? Did you observe some biases that you introduce with these constraints?
Yeah, so the interesting thing is if you detect the planar patches with a plane extractor, right, even if it's not perfectly planar, you might still get a subset of the surface. So you can still use that to establish the matches, but if it's getting too curvy, you're introducing some problems later in the optimization because your constraints are going to be slightly wrong. So it's a bit of a tricky thing to kind of how to weight it, right? Basically, you have a threshold. Do you still count it as a plane versus not? In this case, we were just very strict. We basically, we didn't allow for much variation, so we were more conservative on not taking the matches. This turned out to perform pretty well at the end then.
Okay, thank you.
Yes, there's a question up there.
Thank you for the presentation. The coplanar constraint is a nice one, but it's maybe a bit strong. There's not necessarily a lot of coplanar scenes, but surfaces in a scene, but there's a lot of parallel surfaces in a scene. I'm wondering, did you explore, essentially relaxing your constraint a little bit?
I agree. It's actually not only parallel constraints you could use. You could also use orthogonal constraints. You have rectangles a lot, right? We didn't go so far. So this was, one of the first works where we did actually planar matching. But I think for future work, it would be fantastic if we could have more additional high-level constraints to encode the structure of an environment. And as you said, parallel and orthogonal would be a great start here.
Okay, let's thank Matthias once more.